A particle which has a terminal velocity rather lower than its neighbours doesn't always get left behind. If it did, it would find itself isolated and would fall faster and therefore catch up the rest. The left box has many particles. They are close together and the boundary is sharp. The right box has few particles. They fall with less influence on one another and the boundary is less sharp and travels faster. When the moving body is not spherical, the resistance is not the same in all directions of motion. These identical rods are held so that the bottom of the vertical one is at the same level as the horizontal one. When released simultaneously, the horizontal one travels half as fast as the vertical one. At low Reynolds number, they have just half as much resistance to longitudinal motion as they have when moving perpendicular to their axes at the same speed. This is a property common to all long, thin bodies of revolution. When a rod falls obliquely, it drifts to one side. At terminal speed, the net weight is just balanced by the drag, which therefore acts vertically. The drag may be regarded as being the resultant of two forces, one parallel to the long axis and one perpendicular to it. These two forces are represented by CA and BC in the triangle of force ABC. Remember that a force moves the cylinder one half as fast when applied in the transverse direction as when applied longitudinally. The triangle of velocities can therefore be constructed by bisecting BC at the point D. AC and CD are the velocity components. AD then represents the direction of motion when the cylinder is falling in the inclined position. To find the largest possible angle of the flight path to the vertical, this geometrical construction can be materialized using a draftsman's square and two drawing pins. The pins are placed at C and a point F situated vertically above C at a distance equal to AB. This square can be moved round so that its two perpendicular edges are in contact with the pins. The axis of the cylindrical falling body coincides with the lower edge of the square. The flight path is then the line joining the corner of the square with the point E, situated vertically below C at a distance equal to CF, lies at 35 degrees to the horizontal. I want to draw your attention specially to this experiment because it has an important bearing on why it is that microscopic animals can swim. All the familiar self-propelling bodies owe their thrust to inertial reaction of air or water to the motion of their propelling mechanisms.
The propeller of a motorboat is an example. Here the water which is thrown backwards forms a well-defined wake. The body and tail of a fish form another example, but here the wake is not so well defined. Even a snake swims by moving its body so that each section of it is pushed forward by inertial reaction as the waves of bending move them obliquely in the water. All those we have seen have Reynolds numbers of order thousands or even millions. Microscopic creatures which may have Reynolds numbers as low as 1/10,000 cannot derive any appreciable thrust from inertia. They rely on moving their bodies in such a way that they derive their thrust from viscous stresses. The tails of these bull spermatozoa move like those of tadpoles or snakes by sending waves of bending backwards so that each section moves obliquely in the fluid. Here, however, the viscous reaction to the motion pushes on the tails in the same way that it pushed on the obliquely falling rod. To illustrate the difference between inertial and viscous propulsion, I have constructed two models, both operated by the same source of power, a twisted elastic band. In this model, a rudder-like tail oscillates about a hinge at the rear. Waving the rudder of a boat is so well known as a method of propulsion that the rules of yacht racing legislate against it. Putting this model in water shows us why. But when the model is put into syrup, it cannot move. Owing to the reversibility of low Reynolds number flow, the forward motion of the blade is neutralized by the backward motion. This spiral model does swim. Each element of the spiral is behaving like the obliquely falling rod. Because lateral resistance is greater than longitudinal, motion at right angles to the axis of the spiral can contribute to a longitudinal component. The spirals are right and left-handed to keep the model from rotating. The last example I will show of low Reynolds number flow is that between two parallel plates separated by a very small gap. This arrangement, known as the Healy-Shaw cell, has a special interest because, paradoxically, it offers a means for making visible the streamlines in certain cases of ideal flow of a non-viscous fluid.